May I have your conference ID number, please? May I have your conference ID number, please?
Variety of technical training courses at its headquarters in Research Triangle Park, North Carolina, and other regional locations across the country. With world-class instruction and laboratories containing equipment donated by leading companies in the industry, you will learn from the leaders in instrumentation, systems, and automation. Increases your employees' competency.
Good day, everyone, and welcome to ISA's web seminar, CSE PE Exam Review, Part 3, Measurement 2. Your seminar materials include a downloadable presentation, a question and answer session, and a Zoomerang seminar survey, which will be sent to your email box to complete immediately following the seminar. You earn 1 PDH for attending. Also, as a note for attendees, this seminar will be recorded. Today's seminar is 60 minutes in length. There will be 3 10-minute question and answer sessions. As a participant, you are in a listen-only mode. You may ask questions via the Internet using your keyboard at any time during the presentation. However, the presenter may decide to wait to answer your question until the next Q&A session. If you have audio difficulties, press star 0. Questions may be asked via your telephone line. Press the star 1 key on your telephone keypad to ask a question. If there are no other callers on the line, the operator will announce your name and affiliation to the audience and then ask for your question. If other participants are asking questions, you will be placed into a queue until you are first in line. While in queue, you will be in a listen-only mode until the operator indicates that your phone has been activated. The operator will announce your name and affiliation and then ask for your question. We will now begin today's seminar with a brief introduction of our speaker, Mr. Gerald Wilbanks. Gerald Wilbanks, PE, is Vice President of Documentation and Engineering Services, DES, in Birmingham, Alabama. He has over 40 years of experience in control systems engineering, personnel management, quality systems consulting, and instrumentation design in heavy industry. His experience includes the chemical, pulp, and paper, power, and manufacturing fields. Prior to forming DES, he was associated with Rust Engineering and Union Carbide. He is a registered professional engineer in 4 states, a member of NSPE, ASQ, and an international former president, 1995, of the International Society of Automation, ISA. Gerald is a graduate of the Mississippi State University with a bachelor's degree in electrical engineering and was considered as the Engineer of the Year in 1991 by the Engineering Council of Birmingham. He is a Distinguished Engineering Fellow of MSU and is a Life Fellow member of ISA. He has served as an instructor in many courses, seminars, and other educational sessions for ISA and in his own business. And now, Mr. Gerald Wilbanks.
Thank you very much, Benita, and I'd like to greet everyone and welcome you to this 3rd seminar in our 6-part web seminar series dealing with the review of the materials that are involved with the registration and licensure as a professional engineer and the exam that's required for that. And we certainly want to welcome each of you. Thank you for participating. And many of you have been on here before, some this might be your first time. And again, we're glad to have you, and I commend each of you for taking the time and showing the initiative to work with the materials and to look at and be concerned with your licensure as a professional engineer in controlled systems. Today's seminar, we want to certainly help you be more effective as you attempt and as you pass the PE exam. Today we're going to focus on measurement, the second part, today on flow, on level, and on temperature. We looked at pressure in our prior section, and today we'll be focusing primarily on these 3 parts and some of the common parts that will be related to other domains within the exam itself, but this is all part of the domain 1, which is a total of 20% of the exam. So these questions just for these 3 areas would probably represent maybe 12 questions or about 15% of the control systems exam. So let's begin today. Let's talk about flow first. We're going to look at various terminologies. What are we talking about? We're talking about measuring flow. How do we go about selecting some flow devices? How do we classify flow measurement and some of our applications and some installation? Now, we won't get heavy into a lot of theory, but just to say in fluid dynamics, this is a basic Darcy formula that you look at in fluid dynamics, showing the pressure drop in feet of fluid flowing through a pipe and how it's related to the fanning friction factor, of course, the length of the pipe. Notice we have a factor of V, velocity of the fluid, which is squared, and then that's divided by the inside diameter of the pipe and involved with the acceleration due to gravity. Notice the square root function on velocity is related to the differential or the drop in head, and that's how we'll see later on how we get into the square root relationships in certain types of flow measurement. So this is a basic fluid dynamic equation for flow. Now, if you go through a lot of derivation and a lot of theoretical mathematical calculations, you can come out with a couple of formulas that will be very useful to us, and this is one of them, where we're talking about the measurement unit to express the rate of flow is the velocity. In other words, how fast is a particle of a substance moving over a given period of time. This is one of the common things that we talk about, the velocity of the flow rate of a fluid, whether it's liquid or it's gas or steam. And the basic equation, if you go back and work through a lot of the Darcy situations there, is Q is equal to AV, where the volumetric flow rate is equal to the area of the pipe times the fluid velocity. And we will use this as a basis for a lot of the measurement techniques and technology that you use for flow. Right below this, you will see that I have put in a second equation that says that Q is equal to 3.12 times AV. This is true when you're dealing with gallons per minute. The area is in square inches, and the velocity is in feet per second, which is our normal units that we use a lot for this particular equation. So what I've done is work out to 3.12, a numerical constant, taking into account feet, inches, seconds, minutes, etc., so that we don't have to do that every time we make a calculation. But do remember this basic equation. Q is equal to AV, and it will be the basis for a lot of our flow measurement. And we talk a lot about volumetric flow, and here we're talking about a volume, how much volume is passing a point over a period of time. And we will hear people talk about the volumetric flow rate. Well, normally we're talking about gallons per minute, GPM for liquids, or if we're dealing with gases, we will see it done in cubic feet per hour, either standard cubic feet per minute, standard cubic feet per hour, or actual. We'll talk about some of that a little bit later on. But volumetric flow rate we use quite a bit. Also, though, we talk about mass flow rate. And as the name indicates, mass flow rate is determining the amount of mass that passes a specific point over a period of time. In other words, the weight that's flowing through the system. And the mass flow rate of a liquid would be the density times the volumetric flow rate, would give you, in other words, the volumetric flow rate would be equal to the density times the area times the velocity. And so we will be talking on occasion about mass flow. That will come up in some of the situations we look at. And, of course, in steam flow, we normally talk about pounds per hour, which would be the weight pounds per hour that's actually passing. A critical factor that we need to understand is what a flow, what it looks like in the line, and a relationship of a factor called a Reynolds number. The Reynolds number basically is the ratio of the liquid's inertial forces to its drag forces, and it has to do as the flow is proceeding down the line. And we can look here at this particular situation, and we can see how our flow is proceeding left to right, and we see the velocity profiles actually here, and some of these are related, relational, and we really don't like those. For instance, the one that we denote as laminar flow, you can see that the velocity, if you look at a velocity profile from the wall out to the center of the pipe, there's a lot of difference in the velocity at the center of the pipe than there is against the flow. And that can be symmetrical or it can be asymmetrical, as we see here, shifted up and down. But in any case, the velocity profile, how fast are we moving, really varies as a function of our location across the pipe. Now, this can be very detrimental to measuring a flow rate using several different types of instruments and technologies. And in fact, it's very critical that we end up, as far as flow measurement, with what's called a turbulent flow pattern. And here you can see, as you go across the pipe, your velocity does not change as much. And this is based on the fact of the drag forces, the inertial forces versus the drag forces as the material moves down the pipe. So we want to be very sensitive to that, and actually we can calculate the Reynolds number for any situations that we may encounter. We can calculate the Reynolds number, which is a dimensionless number that's related to this equation here. As you can see, the Reynolds number is going to be a direct function, naturally, of the flow rate, also of the specific gravity, will give a higher Reynolds number, whereas the diameter, inside diameter of the pipe, will be a negative factor on that. And then we have a factor here that's actually very important, the fluid's viscosity. And as you can see, it's in the denominator of this particular equation, so it has a real heavy effect on the Reynolds number, so that the higher viscosity liquid will give you a lower Reynolds number. In other words, if I have a Reynolds number of 30,000 with water flowing, which has a viscosity of 1 centipoise, I change that flow rate out, flow material out to a heavy, high viscosity. Well, not heavy, let's just say it has a viscosity of 3. I immediately cut my Reynolds number from 30,000 down to 10,000, which is a drastic impact, as you can see. So viscosity plays a heavy factor in there. So we have 3 regions that we talk about, that we look at. One is called the laminar region, and that is where our actual Reynolds number is very low. Then we also have an area called the turbulent region, which is actually what we want to have. We would like to get a Reynolds number above 4,000. Actually, in some materials, in some books that you will read, you'd like to get it up in the 8 to 10,000, because you are still, when you're between 2 and 4, or even up to 6 or 8, you can still be in what's called the transitional region, and you could see that that is an area that we don't want to be in because of the velocity profiles that we looked at earlier. So typically, the higher the Reynolds number, the better our velocity profile is, our better chances of making an effective measurement of flow. Let's classify our flow measurements into 4 categories: inferential, velocity, volumetric, and mass. And very briefly and quickly, we're going to move through these so you can see how these things relate to each other. First one that I'm going to mention here is the differential pressure measurement. And the differential pressure type measurements come in many different forms, but basically they can be used to measure the volumetric flow rate of liquids, gases, and vapors, including steam. Now, as we'll look at a little bit later, typically there might be some limitations because of suspended solids in the stream. Maybe viscosity might play a hand. Certainly Reynolds number has to be looked at. However, they're very simple. They have no moving parts. They're easy to use. They do create a non-recoverable pressure loss, and they lose actually if you foul them. Now, the non-recoverable pressure loss is to be expected, because to have a differential pressure, naturally, you've got to have a restriction of some nature in the line that does drop a pressure as you increase velocity moving down the line. But that change in pressure, or the differential, is predictable and can be used as flow measurement, and it is used in many cases by several different devices. The accuracy, of course, also depends on the accuracy of the differential pressure or the pressure measuring device itself. So you've got to have the sensor, which is a differential pressure restriction in the line, and then you measure the differential pressure as far as determining what that flow rate is, which is predictable according to the type of measurement that you may be making. We'll point out here, let's look first at a differential flow measurement. As you can see, we have a restriction in the line. In this case, maybe it's an orifice plate, but it's a restriction. And it has a little d bore, which is smaller than the big D inside diameter of the pipe. And what we will be interested in is measuring the difference between an upstream and a downstream pressure. That will be our differential pressure, and will be based on the amount of flow going through the bore, or little d, or diameter of the bore, as well as the overall big D, or the pipe ID. But there's different types of devices that can be used and are very helpful in measuring using differential flow. Here's another, this is a pressure profile, not a velocity profile, but a pressure profile, which is indicating the pressure as the flow comes down the line and right at the face of the plate, and then we go through the restriction or the primary element, which might be an orifice plate or some other type of differential pressure device. And at that point, we will have a drop in pressure due to the increased velocity. As the way I look at it, or tell a lot of people, if we have 100 gallons per minute here, what's my flow rate here? And it's going to be 100 gallons per minute downstream. And that's also the flow rate that's going right through the primary element. Well, if our number of gallons per minute is the same, you remember Q is equal to AV. The only thing that's changed is the area. And what happens is, as that area becomes smaller, our velocity does what? It rises. Our velocity increases. And just like you move an electrical current through a resistor in an electrical network, we have a pressure drop instead of a voltage drop. So here we're looking at a pressure profile of this moving through. You can see the recovery downstream. It recovers up to a point, but it never does recover back up to the point that you were, for instance, right at the impact to the pressure dropping device. But in this case, your flow rate, the velocity increases, the pressure drops. If you recall back to that Darcy equation, where the velocity squared entered into the drop, the H. So if you to actually determine the volumetric flow rate, it's going to be based on the square root of the differential. It's a very critical factor when you're dealing with pressure differentials as far as flow measurement, that it is based on a square root function that we'll look at a little bit later on. The orifice plate is the most common one of these. Notice a key factor I think we need to look at. It's normally for clean liquids, gases, and relatively low velocity steam flows. They are relatively economical. They're simple. They're easy to understand. So you'll see a lot of these in many industries. Other industries you may not see as many of, but the orifice plate is a differential pressure producing device. This is showing a view from the, actually looking down the pipe, where you can see the inside pipe diameter and the bore of our orifice plate. And again, you can see as the flow comes through the plate in this direction, the relationship between the overall diameter and the little diameter. And this is showing the thickness of the plate, which normally will be something like could be down as low as 1/8 of an inch. Normally it's 3/16 to a 1/2 inch, depending on the pipe size. Then the downstream edges are beveled so that the flow goes through the sharp edge and then out the beveled side. If there'll be some information that would be on the upstream face, such as tag number, bore, some identification like that. You want to make sure you always have the orifice plate installed with the flow in the correct direction. If you do not, your differential pressure will not be as predictable, and you will probably get a lower drop for a higher flow. In other words, you will have an error. So you got to make sure they're installed properly. There's several different intricacies we won't have time to talk about, such as a eccentric plate. There's also a segmental plate, and there are occasions where you might see what's called a little 1/8-inch hole either at the bottom of the line when you're flowing gas, so that liquids might drop out and would actually drain down the line. Or if you have a gaseous flow, you might have a small 1/8-inch hole at the top of the pipe in the plate, so that any gases that are formed may vent down the line. These are called a drain hole and a vent hole. But again, we could spend a lot of time talking about orifice plates. They're very common. You see them in many, many industries. Then we have to look at, well, where do we check this pressure? Different types of taps. On some larger lines, many people prefer to go what's called the radius of vena contracta taps that are actually about D and D over 2 with respect to upstream and downstream. And this is actually measuring the incoming pressure to the differential pressure device, and then looking at the pressure at the vena contracta, which is the lowest point of pressure. If you go back to the earlier slide, the vena contracta would be in this area right here. That is the point of lowest pressure. So we actually, with the vena contracta or radius taps, we are checking that particular pressure. So you see these used particularly on lines above 6 inches in diameter. On some of the smaller lines, we may go to what's called flange taps, and on flange taps you drill, or they are drilled actually right into the flange themselves, where 300-pound flanges are used, and you measure the differential with these taps right across the orifice plate. So these are very useful, and particularly for line sizes maybe that's 8 inch and smaller, maybe 6 inches and smaller. It depends on, again, how this particular company or this particular facility likes to handle their orifice plates as well as their taps are concerned. So we see here how these are set up, and then to recognize, could be on the exam, you might have to recognize another type of taps called pipe taps. And while the vena contracta radius taps were taps in the pipe, this is a particular type of tap where you have the upstream tap is 2.5 pipe diameters, the downstream tap is 8 diameters, and effectively what you're doing with pipe taps is you're measuring that permanent pressure drop. Again, if you go back to the picture that we showed here with the pressure profile, the pipe taps are really measuring the pressure down at this point and this point, whereas if you're dealing with the vena contracta, you're measuring the pressure here and here. So you've got two different sets of relationships, two different kinds of situations as far as the drops are concerned, two definitely different types of calculations that are concerned. But these are different types. There's other types of taps that can get involved. These are our most common. In your summary of equations, most of you have that we sent out after the first session. If you look at your summary of equations, there's areas there that has this equation, which is a good way to size an orifice plate. It's calculation for a S value, which then you can look in the back of the summary of equations, and you can find a beta ratio, which the beta ratio actually can be multiplied times the pipe ID, and that will give you the actual inside, or the bore, or little d, for the particular orifice plate. And as you can see here, and I think we show it maybe better, a little bit better in another slide, but you can see the information that you need to have as far as making this calculation. And these are the terminology definitions here. Beta ratio is little d over big D. Normally speaking, because of the restrictions of empirical data, that's going to be limited about to 0.25 to 0.75. We also will note we have the little d, the big D, the flow rates in gallons per minute, the specific gravity, we talked about that in another session. That's the flowing specific gravity, the base specific gravity, which is at 60 degrees, a unit constant for liquids, and then we talk about pressure drop most time in inches of water. When we talk about the pressure drop across a differential unit, it's usually in inches of water. For instance, for the liquid, 0 to maybe 100 inches of water, which is about 3.6, 3.7 psi. The recovery on that, if you were running full bore and recovered maybe 50 or 60%, you might have a permanent loss of a pound and a quarter. Under normal operating conditions, maybe a half a pound, 3/4 of a pound, because you do recover a portion of that pressure drop, but there is a non-recoverable loss also. Now, the S value, again, that comes from the LK Spink book, but it's also, it is in your summary of equations. There's some tables in the back of the book that you can use and directly go about calculating the bore for a liquid flow. Here's an alternate equation that you probably won't find anywhere else, I don't think, except because this was derived from the Cameron hydraulic book. And basically, we broke the equation up into two parts to where you take your, you calculate a K, which is based on the flow rate Q and the differential H. Notice this differential, though, is in feet of liquid. Again, this equation is in the back of your book in your summary of equations. You have a couple other factors in here that are pretty straightforward. The C is normally 0.61 for sharp edge orifice, and F sub A, unless you have very high temperature, it's going to be 1. So what you can do with this equation is you calculate a K, then that K is plugged into this second location equation, which takes into account the inside diameter of the pipe, and again your K is plugged in, and you calculate the bore of the orifice plate directly by taking the fourth root of this particular equation. Again, this is real handy. It's not precise, but we have done checks on this equation versus the Spink equation versus running it on a computer, and it's amazing the relationships and how close they will agree with each other. So this is the way that if you were to have to size the orifice plate, it gives you a chance to do that. Here's the plant equation, again, from the Spink book. This is, again, a S calculation. Notice here now you're dealing with steam and gas, and you have a factor that comes into play called specific weight. And that, of course, is going to be pounds per cubic foot. Pounds per cubic foot. Now, that will be plugged into the equation. Notice, again, you have the square root function of this particular, this drop, which is H. This H actually is in inches of, excuse me, it's still this is in inches of water for this particular one. And the 359 is a numerical constant, and then you have the inside diameter of the pipe squared. So again, you can go to the back of your book, look up the S, get you a beta ratio, multiply this out for your particular calculation. So these two equations for the liquids, and then also over here for the steam or gas can be very useful as far as calculations for the sizing of an orifice plate. Real briefly, let's go through a few other devices that you will see for measuring flow. This is a flow nozzle. The flow nozzle, of course, you can see is rather streamlined, but you still have an upstream and downstream differential pressure measurement as the flow comes in this direction through, but the shape or the design or what you have on the inside is much more streamlined, and sort of it's very useful for large lines, high velocities, high pressure high velocity steam, for instance, or other types of measurement, because for the same amount of flow, you get quite a bit lower drop in the flow nozzle than you do in a corresponding orifice plate. And so these can be used in many cases for flow measurement, or a venturi tube, much along the same line. Again, you have the upstream tap and you have a throat tap. These can be used a lot in very large sizes, are very useful for different types of measurement. Some amount of suspended solids can be handled here because you do have a streamlined throat flow area and so on that makes it very handy. Pitot tube is used many times. An averaging pitot tube becomes more handy because this really describes and shows how the velocity, where you check the velocity, will greatly depend upon, and the way we looked at that a little earlier with that velocity profile, if it is something like this, then depending upon the physical location of this pitot tube, it can affect your measurement. But again, it's a differential pressure producing device used in many cases. Again, an averaging type is used where you actually extend the tube across the pipe with several different holes. So that's some of your major types of inferential measurement type, and there's others that we simply don't have time to cover today. Let's look at some velocity measurements. One of the types is a magnetic flow meter. Magnetic flow meter actually sets up a magnetic field across the pipeline. You actually set this up, and then the fluid flow itself must be conductive, and as that fluid flow moves through the magnetic field, depending on the velocity of it, it generates an EMF that is picked up by the sensing electrode, and then that's converted to a milliamp signal, which is proportional to the flow rate. So here, whereas the differential pressure units was inferential because of measuring differential pressure, we're actually measuring velocity here. But since we also know the area of the pipe, and we remember or we know that Q, the volumetric flow rate, is equal to what? It's equal to the area times the velocity. So if we know the area, measure the velocity, then we have volumetric flow rate. They tie together like that. So for slurries, liquids, suspended solids, these are just some application notes that could be problems on the exam, some type of a scenario problem. You have to have the meter must be full. You've got a flowing material conductive. It must have a conductivity value that lends itself to the generation of the electrical value there by the velocity moving through. Very minimal straight run requirements, but you do have to make sure that you're grounded properly and make sure that you are actually got this installed properly for it to operate. So these are some of the situations that you would need to take into account, and mag meters are very, very useful. Also, when you talk about velocity, vortex shedding, vortex meters, where a bluff body is placed into the line, again, is some sort of restriction, and depending on the velocity moving down the line of the liquid, the gas, or the steam, you generate vortices are formed, the frequency of which is based upon the velocity, magnitude of the velocity of the fluid moving down the pipe. If you look at it, it's called the von Karman effect. This is showing the flow impinging upon the bluff body, and the swirls or the vortexes that are formed. The frequency of these are picked up and can be used as an indication of the frequency. The frequency of the vortices is an indication of the velocity of the fluid moving down the line, and then by knowing that velocity, we know the area, and again, Q is equal to AV, and we're able to make the determination of the flow measurement. Many people like to use ultrasonics, either Doppler or time of flight. You might have a scenario where you would need an ultrasonic flow meter. You can have them in clamp-on, They can be wetted. They have certain limitations, but they certain places, applications like the large pipes, flashing or corrosive fluids, they're very, very useful in certain types of industries, certain types of plants or locations. So again, they have to be applied properly and used properly, but they can be, the time of flight is one way, either clamp on or the wetted transducer, and the acoustic beam and the measurement of the direction there can tell you as long as there's particles within the stream, or it can be installed in the same type of measurement for the time of flight, or the Doppler effect is used in many cases. Again, notice that basically you're external to the pipe, and the reflected material depends upon the velocity of the material moving along. Notice again, we're still interested in that velocity profile. We're looking at the velocity of the fluid, and that velocity is also critical as far as being able to have a good flow measurement determined. The turbine flow meter is used, and many of you may be familiar with these. It's basically a rotor in a line, and as the material comes through, that rotor spins. The faster or the higher the rate, higher the velocity, the faster the rotor spins. Therefore, we pick that up with a sensor, and again, multiply the velocity times the cross-sectional area of the turbine, provides a volumetric flow rate. So it's very, very accurate, very useful in certain areas for that. The mass flow meter, there's only a couple of different ways of measuring mass flow directly. The Coriolis mass flow meter was brought into place several years back. There's a thermal mass flow meter for gases, but we'll just mention this one here, Coriolis, where the flow comes through a vibrating tube. Vibration is set up, and as the flow moves through, the fluid forces react with the vibrating flow tube and actually produce upward and downward forces. The net result is a twist angle, and this twist angle is directly proportional to the mass flow going through this device. It was originally introduced by Micromotion. I think the patent is now expired, and many people make these. They're very, very accurate. They're very useful in certain situations as a flow measurement device, and so we show them here. These are some of the attributes of the Coriolis flow meter. Notice one thing, the high turn down. This is a good time to mention turn down. When we talk about turn down, we're talking about the ratio of the maximum measurement that can be made at a specified percent of accuracy to the minimal amount that can be measured with that same degree of accuracy. To give you a little confirmation on this, while 101 sounds a little bit high to me for Coriolis, but it is something like 50 to 1, okay? And the orifice plate is 3 to 1. That means on an orifice plate, if you want to measure 100 gallons a minute with as accurately as you can, once you get below about 30 gallons a minute, you're still measuring it, but your accuracy starts degrading. Notice here on the Coriolis, 100 gallons a minute might go down to like 1 gallon a minute. But this is showing some application points. You might make a note of these and be aware of that. And just real briefly, the the positive displacement flow meter is the only way I know of to directly measure volumetric flow rate. Any other measurements will be some sort of differential pressure or velocity or whatever, but in a positive displacement meter, which you're very familiar with them at gas stations or water coming into your home or whatever, vanes, gears, and pistons are actually used. Separate the fluid in little packages of a certain volume, and therefore the faster that moves through, they're really the only device that directly measures volumetric flow. They are mechanical. They do have moving parts. They are subject to wear, of course, but you can measure positive displacement by using some of these meters. This is just showing a rotary vane design of how the material comes through. It actually is rotated through in a measured package of volume, and continues on down the line. Different meters do require different amounts of straight run. That's so that you can have less disturbance or turbulence in the flow rate. Notice a orifice plate might need 10 to 15 upstream and maybe 5 down, while a magnetic flow meter requires much less. The Coriolis requires basically none. You do need to be aware of that in case there's a question about straight run requirements. And while these are rules of thumb, they definitely can come into play and might be involved in a question. This chart you have in your handout is an application chart. You will notice on the left-hand side you have, and you can read these for yourself, a lot of different types of meters, and then across the top you have applications, and then you have features of the meters. For instance, notice over here for the orifice plate, integral orifice, and many others, the square root function. That means that the flow rate is proportional to the square root of the differential, while other devices are directly linear, like magnetic flow meter, rotometer, turbine. So this is a good reference, and also you will notice here you have a good ranking of your rangeabilities. That's the turn-down ratios that I was talking about a little bit earlier, and then look at the Reynolds number requirements that some of these meters have. That's why you have to do a calculation of the Reynolds number many times to make sure that you have sufficient velocity, you have the flow pattern such that you can make a meaningful measurement. So we offer that as something for you to look at and take as far as a reference document is concerned. As far as installation, you recall back we talked about pressure. For liquid or steam, we're going to prefer, we want to mount this below the connections there so that if there's any gas formed in the vapor, it would go back up into the line. And this is just showing that in a format with our differential pressure transmitter out here to the side. And we've got our lines coming down and so on and so forth. This would be how we would install on liquid or steam, or if we had it on air and gas, notice this time we're mounting our differential pressure or pressure units above the tap so that any liquid or condensables that may be formed in our vapor line, air or gas lines, will drain back into the line. So these are just a couple of installation details for your reference on how to install devices. I know that was a pretty good pull there. The flow measurement is very, very important. There's many, many ways to measure flow. Differential pressure is economical, but has some drawbacks. A lot of these devices are inferential. You do need to take into account straight runs. We talk about volumetric flow rates, so you need to determine, are you talking about, gallons per minute or pounds per hour? Is it a mass flow? There's a lot of new state-of-the-art devices and improved devices in play. You need to know installation requirements, and you'll probably have some scenario situations on the exam that will give you a flow type or situation and have you select the best device for it. Okay, Bonita, let's pause now for just a couple of minutes and see if there's any questions.
Thank you. At this time, please press star 1 on your telephone keypad to ask a question. There's a question from the line of Charles.
All right, go ahead, Charles.
And he's from Progress Energy.
All right, thank you. Go ahead.
I typed it in also, but when I was looking at the formulas on the slide you had given for liquid flow alternative equation.
Yes, sir.
The K, right?
Yes, K.
The formula is different than what was on page 6 of the equation and terms handout that you had emailed out.
Okay.
Working through some of the problems, I found that in the denominator you have the 19.636, and in the handout it was 9.636.
Oh, it's supposed to be 19. It is supposed to be 19. Let's see, I was trying to go back there. I could see that. Let's see. I'm at the, let's see, excuse me just a minute. I'm sort of stumbling around here.
The slide here is correct.
Yeah, this is correct. And you say the one that I sent out only had 9.63 on it.
That's what I saw when I printed it.
Ooh, I need to check that. I appreciate you pointing that out. The 19.636 is correct, okay? So anybody else, if you have those, I'll go back and check those, and that may be a little mistake in the last time. We made some modifications to that, and I may have messed that up, but it should be 19.63. Thank you for pointing that out.
Yeah, because I found it when I was working through some of the problems that I've been working on.
It would make a little bit of difference, to say the least.
That's true.
Thank you very much.
There are no further questions on the phone.
All right, very good. I appreciate that. And like I said, anytime you have a comment or a suggestion like that, I would appreciate you just sharing that with everybody, because we do make a mistake every once in a while, like every day when I do anything. But anyway, I would like to go ahead now and give you my email address. I use this one to communicate with most of the people dealing with the PE exam, gwillbank@aol.com, and right now you have a set of sample problems, number 1, I believe. I've got a sample problem set number 2, I guess it'd be, and you should have a summary of equations, a bibliography of references, sample problems number 1, and sample problems and this will be sample problem number 2. So if you will send me an email to this address and say send me sample problems number 2, I will be glad to respond to that, and I'll be happy to give you that. So write that down and record that, and we'll move on into measuring level, which is our second topic today. Flow topic is a wide topic. Level topic is wide. We'll make up a little bit of time on temperature a little bit later on, but we want to treat all of these. Level, we're just trying to see where something is, or maybe it's how much is in a tank, a vessel, some sort of storage container. It could be solids, it could be liquids. We talk about liquid level a lot, but it could be solids, it could be, and actually it's the interface point. It's actually the interface between a liquid and a gas, or a solid and a gas, or it could be the interface point between two liquids. But we want to know what that is, either for operational purposes or perhaps we need it for inventory measurement. This is just a partial list of some of the ones that you can have. We're going to talk about a couple of these, but we don't have time to do too many in this. There's entire books written on measuring level, entire books written on measuring flow. This is just a brief overview. Differential pressure, hydraulic head, we'll use hydraulic head to measure level just like in flow. Capacitance probes, which is variance in capacitance as the material goes up and down. Ultrasonic is used many times in tanks if you have the proper type of environmental conditions within the vessel. Radar, guided wave radar, both guided wave and through air radar, different types of floats and displacers, nuclear radiation, rotating paddles, gauge glasses, and you can go on with many others. These are just magnetostriction and other types, and I'm just mentioning these so that you may go back and sort of review a little bit and determine some of the ways that ones that you may not be as familiar with, and take a look at those. Capacitance probe, just as we show here, the capacitance will vary between the two probes, whether you have two probes or a probe and a metal wall, as the level rises and drops in the tank. And of course you can have coating and buildup on the probe. You got to have certain types of material that's fairly constant. So there's some limitations on that. And of course it is inserted into a tank as this type of measurement, which is the old float type. Basically it's a float that rides on the surface of the liquid, and it can either drive like a board up and down the side of a large water storage tank, or it can actually move a rotational type situation, which can generate an output milliamps, or it can be other types of floats. But float devices actually are designed, and they're sized, and they're balanced with the specific gravity to actually float on the surface of the liquid, and it's very critical in that design. The ultrasonic we mentioned has gained a lot of popularity in past years, and you have a generator, the transducers, they check the transmitted burst time, and then they check the received burst that's reflected back, and by looking at that elapsed time being proportional to the distance, you can get an indication of the level in this particular vessel. You would have to be careful of several things that can give you problems here. Foam on the surface could be a problem. If you have a lot of suspended solids or maybe dust or whatever in the atmosphere in the tank, that could cause a problem with the measurement. Changing different types of materials could be a problem. But, you know, within some certain bounds, it can be a very effective way to measure level. This slide basically is depicting the guided wave radar, where you have a situation that actually the energy is guided by probe down into the vessel, and you get most of the usable energy that's returned back up to the sensor. Also, you're not affected by some of the other things that you can have a problem with, like different types of interferences, ladders in the tank, bubbles on the surface. Foam doesn't really bother it very much, and it's a little bit more effective in some cases than the through air. The through air, of course, is fine. It's a non-contact type. You do have to have it aligned pretty close. Again, it does good if it's fairly clean environment with very little foam maybe, but you also got to be aware of any interferences within the tank. But both of them are the radar type sensing, and become very popular in recent years, or I say recent, over the last 10 or 15 years, and are used in many different types of applications to measure level in rather difficult circumstances. Now, this is sort of a goldie but oldie. You hear about air bubble systems, dip tubes, bubble pipes, as the case may be. Basically, you'll see these. They can be used. This could be an underground sump, for instance, is one thing you could use them for, but it's still a differential pressure measurement. You have a specified area that you're going to cover, and the back at the location, we don't show that so much here, but you have a rotometer, and you just set that up to maintain a flow rate, and the bubbles will come out, and the regulator will adjust the pressure sufficiently to allow the bubbles to be escaping, and the pressure that allows the bubbles to escape is reflected back up toward our indicator recorder, so that we actually get a measurement of the actual height that we have above the bottom, or if you will, the outlet of the dip tube. Very reliable, old, dependable, as I said, goldie but oldie. Used a lot in some industries, not very much in others, but it's still a differential pressure, inches of water type transmitter situation. The magnetostriction that I mentioned earlier is used in some cases. Now, it's based on a waveguide with a float that rides up and down on the material. This has a magnet within it, and the magnet is, the float magnets ride up and down in the float. The magnetic field from the float magnets interact with this waveguide and actually gives a twist to it, and the torsional pulse travels in both directions, and they convert the time of travel to level. So it works by the intersection of the magnetic field and the permanent magnet, and so you actually, as you come down, this actually reflects back. So the magnetostriction is a combination of electrical, but it's also a float actuated device. Again, you've got mechanical materials within a tank, within a vessel. That's one of the drawbacks, but it's very effective, fairly economical, used by a lot of people. As we've talked along here, some of the factors that you have to consider: what kind of vessel are you dealing with, what specific gravity. We've got to look at Pascal, Boyle, and Charles's law too, the ideal gas law, and also the law that says that when you impose a pressure on an enclosed vessel, that pressure will be transmitted equally throughout the container. And so that's how we operate with our differential pressure, our high and low pressure on that. Also, what type of material do we have in the tank? What's the environmental considerations? Are there dust within the tank, and so on and so forth? Here, just like we had on the flow, we also want to have something to help us out a little bit on our level. Here's a basis of selection chart that's in your material that came with the seminar. You will notice that you have certain conditions down the left-hand side that list certain conditions that you might want to take into account. For instance, if you have foam, then you look at that, and then you, across left to right, we have certain types of transmitters that you can do an evaluation on. For instance, let's say that you have a situation where you have a changing specific gravity. Notice the differential pressure is ruled out right off the bat. That's how you determine maybe the best one. You look at your application. Do you have a changing specific gravity? Your electrical properties, are they changing? Is there turbulence or foam? High pressure, high temperature? What about the cost, accuracy, etc., etc.? So this, you can probably find tables like this in other locations. So this is just one that you might take that might be handy for you. You will probably have circumstances where you will be given a scenario or some type of a level measurement to make, and they'll ask you to select the best choice. These are some conversion factors that I think you need to have in mind for any of the measurements. This is just physical data that you can find in tables and charts, but I think they come in handy with respect to some of the quick calculations, like 2.31 feet of water is a pound, which is the same as 27.7 inches of water. Mercury is 13.6 times the density of the water. Half a PSI is about an inch of mercury. And notice the 8.33 pounds per weight of a gallon of water, and you can put 7.48 gallons in a cubic foot. And if you multiply them together, you get the real useful term of the overall density of water of 62.4 pounds per cubic foot. So these are some I think you need to either have handy, have them in a table or somewhere that you can look at, because they do come in, may be very convenient for you. If you look at measuring, using differential pressure to measure the level, this is showing a flange-mounted differential pressure transmitter. Actually flange-mounted. This has a shutoff valve also connected onto the tank nozzle. Notice in this particular case that we have vented the low pressure side because it is a vented tank. And when you have a vented tank, of course you don't have to have that. This was a pressurized tank, going back to Boyle's law, and even if you look at the ideal gas law, pressure, PV is equal to RT, and some other things that you run into in compressibles. When you apply pressure on this tank, that pressure must be transmitted or applied both to the low pressure side and the high pressure side, so that they will cancel each other out. So with a vented tank, though, you can vent the low pressure side because atmospheric pressure is your reference at this point. This showing another situation of measuring level using, here's our high pressure connection, our low pressure connection, our differential pressure transmitter. And this is just showing how this would be done as far as a liquid level measurement is concerned. Now, keep in mind you might have a situation where you have to take into account this hydrostatic head by this liquid fill lead that you'll have between the taps in some cases. But this shows representatively how you would do that. You would have liquid in the lower, liquid in the other. You'd have to take that into account on your particular situation. Real quick span and range calculation. Let's look at these three situations, A, B, and C. If we look up here at System A, our low range value, let me do it a different way here, our LRV is going to be equal to what? Well, if you drain that down, notice it's a vented tank in System A. If we drain it, we'll actually end up with 0 inches of water. And if we then look at our URV, which is another terminology we talked about earlier when we talked about transmitters, we need to fill the tank on the 20 inches. The 20 inches times 1.2 will give us 24 inches for our inches of water for our URV. Then if we come over to System B, and let's look at what our LRV will be. What will it be? You're looking at it. What do you think it's going to be? Well, you're going to have 2 inches that you have to take into account. The 2 inches here times what? Specific gravity of 2, so it's going to be 4. LRV is going to be 4 inches of water. So, whoops, I got carried away with my little thing there. So we will have 4 inches of water, okay? And then if we come over here and look at our our URV, what is it going to be? Well, we fill it up, we'll have 20 times 2, specific gravity, we'll have 40, plus the 4, so we'll have 44 inches of water would be our URV with our calibrated range of 4 to 44 inches, which is a suppressed 0 range. Now, if we look at the bottom one down, we have a wet leg filled with specific gravity of 2, so our LRV is going to be equal to, if we drain the tank, we'll have a negative on the low pressure side, a specific gravity of 2 times 20, so we will have a minus 40 inches of water. I'm leaving off water here. I think everybody understands that. And then if we fill it up and look at our URV, what will we have there? There we'll have on the positive side, we have 20 inches of water, which is 1.0 specific gravity. So we'll have 20 on the positive side, but on the negative side, we have what? A minus 40. It's still there, okay? Or that will give us a minus 20 for our overall result. Then gives us calibrated range of minus 40 to minus 20, which is an elevated 0 characteristic. So here you see 3 situations. Let me show you something real quick. If you wanted to know the span of each one of these devices, the span on A is going to be what? 24 inches? 24 inches of water is the span. Notice that we could get that directly by multiplying 20 times the specific gravity. That will always give you the span. No matter where the connection is, no matter if it's elevated, suppressed, same way here, 20 times 2. If you look over at System B, our span is what? 40 inches. So if we go over there to that one, the same way, our span is going to be 40 inches, and you can see the relationship there directly. Then if I came down to the bottom one, and I take 20 times that, times the specific gravity of 1, I would get down there a span equal to what? 20 inches. And if you look right above that, you'll see that that was what the span was. So anytime you have a differential pressure transmitter, you need nothing but the span. Keep in mind, if I multiply the distance between the taps times the specific gravity, I will get the span for that particular transmitter. No matter if it's flange mounted, no matter if it's below or above the taps, it doesn't make any difference to the actual calibrated span. That could come in handy in a particular situation of understanding that particular part there. Okay. So level, again, one of our key primary variables. It's very important. The applications vary according to the physical condition of the vessel and the tank, and you've got to look at coating and fouling and interference and temperature and all different types of characteristics of the material. Does it have a dielectric constant? Is it conductive? And you got to be careful when you apply external transmission type devices, because they can give you problem as far as getting the level in the tank. Of course, there's many that we didn't talk about, like load cells, nuclear radiation, and others. Again, this is to just give you a little flavor and hopefully give you a little review as you head towards the exam. Okay, but anyway, we'll pause again and see if there's any questions or comments now.
Thank you. As a reminder, please press star 1 for questions at this time. Mr. Wilbanks, there are no questions. I apologize.
All right, thank you very much.
I do apologize. We do have Charles Nielsen of Progress Energy.
Okay.
Sorry about that. I was a little late. When you went through the slide with the showing the tanks with the specific gravity,
Yeah.
You know, you showed the wet leg having a specific gravity of 2. Now, I
Yes.
would have made the assumption that the tank would also have a specific gravity of 2 at that point in time.
Okay. This particular case, the way this one was laid out, you'll notice they told us this is water in the tank. And what they've done here is the external leg, the wet leg, somebody has made a conscious decision to put some liquid in that wet leg with a specific gravity of 2. Now, sometimes that's done, they may use ethylene glycol, which is not a 2 specific gravity, but they use the filler material for the wet leg is selected maybe to keep it from freezing or all. But what you generally, in other words, you don't necessarily have the wet leg filled with the same material that's in the tank, because you don't want to depend on the tank to keep that leg full. You want that leg filled all the time, if you follow what I'm saying. And so the material you use there may be entirely different from the actual liquid in the tank.
Right, and I guess it's a case too. Make sure you read the question, right?
Well, that's true. You gotta. That's a good point there. Read it very carefully.
Because once you mentioned that, I saw the H2O in the other part and went, oh, okay.
Yeah. Well, that would be a fast conclusion, and it's like I tell people on the exam too. You know, if on the exam they tell you black is white, that is the case for that particular circumstance. So it might not be exactly logical to you. It might not be what you do in normal practice, but in any event, take that into account. I think the key thing too to take away from this again is you multiply that distance times that specific gravity. That will always give you your span, regardless of what you're doing with wet legs or the transmitter or whatever. I think that's very important. But that's a very good question. I appreciate you bringing that up. And that would just be a case of where they have used a different filled material for that wet leg.
Right. All right. Thank you very much.
Thank you. Appreciate it.
Okay, no further questions at this time.
All right. Thank you very much, and appreciate that. And we'll move from that into our third section today, which is on temperature measurement. And that being another process variable that's very key. I know there'll be some questions involving temperature, or if not exactly the temperature elements and thermometry itself, you will be involved with how to measure temperature, or certainly how to control it, or what type of characteristics it has, etc., etc. So let's brush through these right quick on some samples of things that you might have. First of all, you need to understand temperature, if nothing else, because of the different types of scales you may run into. We're all pretty much familiar with degrees F and degrees C. in other words, Fahrenheit and Celsius scale, and that water will boil at 212 F and 100 degrees C, and the ice will melt or water will freeze at 32 degrees F and 0 degrees C. And so we're pretty much familiar with those. But on occasion, on the exam, you will have circumstances that will require understanding and knowing about degrees R, or Rankine. Rankine is a scale that is related to the Fahrenheit scale, but it's plus 460 degrees. 460 degrees, so you can see very quickly there that the 32 becomes 492, 212 becomes 672. So you need that, and that spreads the scale out from, you see 0 is minus 460 or 459.4. You will see degrees Rankine in some calculations dealing with various gases and fluids of that nature. So it's used in some calculations, and you need to be very mindful of your units. If there's any calculations to be done, be aware that the units you have to convert back and forth in many cases. Notice also we have another type of temperature scale that you can run in, degrees K or Kelvin. Now it's related to the degrees C scale, except it is plus 273 degrees. So you see how it relates as far as the different points are concerned as you move up and down the degrees K. I think Kelvin may be used in some cases in cryogenic industry, but these three, degrees K, degrees C, degrees F, and degrees R, I think you need to be aware of those because you may have to convert back and forth, and you may have to convert back and forth between degrees F and degrees C. So we need to understand the temperature being the degree of hotness, if you will, of a fluid, of a gas, of a vapor, of a liquid. It can be expressed in several different temperature scales, and we need to know the relationship between the two, and we need to be aware of what the statement in a problem, how it is stated, and also keep our units consistent if we do a calculation. So that's the purpose of this situation here, is to let you see that. Real quick, local temperature indicators that you see through a lot of the units, just local indicators, are bimetallic thermometers. They're not transmitters, they're local indicators, and how they're put together is mainly a combination of the junction of a low and a high expansion coefficient metal, then with one end fixed and one end free. As you apply varying temperatures to the fixed end, the difference in the coefficient, expansion coefficients, will cause a twisting motion, which will rotate a shaft moving a dial around a calibrated scale. And that very simply, of course, the scale can be everything from a half inch in diameter to up to 5, 8, 10, 12 inches now, depending on if it's mounted on a panel or on a line or whatever it may be, where it may be located. So these are just local indicators and not really involved in the transmission part. Most of our temperature measurements for transmission, of course, they may be field system transmitters. You don't see as many of those now as you used to, but the types that we're going to focus on here is going to be thermocouple. The thermocouple is the first one to look at, which a measuring junction is set up with the junction of two dissimilar metals. And those dissimilar metals are junctioned at the other end at some reference point, reference temperature, if you will. Normally we use a reference junction temperature of 32 degrees Fahrenheit. That's a freezing point. And as the temperature at the measuring junction goes up, a predictable EMF will be generated. The difference between the temperatures will generate a predictable EMF, and that EMF is relatable to the actual degrees of temperature. Now, if you look at a industrial type, the measuring junction is fabricated into a thermocouple this is brought back to some sort of an instrument at some point that has an electronic reference junction. Then the types of thermocouple that you have will generate a corresponding EMF that can be related to temperature. Thermocouples have a lot of advantages. They're used extensively in some industries, not as much in others. ISA does have standards that shows the standard thermocouple materials that you will be exposed to. You ought to at least be able to recognize a type J as being iron constantan, being the street name of iron over copper nickel. The type K is very common, being nickel 10% chromium over nickel 5% aluminum, which the street name is chromel alumel. A lot of you will recognize that one. And then also the type E. You may see that in some places, which is the chromel constantan. You say, well, why have these different types of thermocouples? Well, notice that they have different characteristics. Notice the chromel alumel will go to a much higher temperature than the corresponding iron constantan will. And so therefore it has a lot of usages in some of the power industry and boiler areas, things like that. And then also in this particular table, they do show some characteristics of these thermocouples, which one are more linear, which one is related to different temperatures. But these are standards. These are ISA standard designations. They do not vary from manufacturer to manufacturer. Here's some others that we see here. T, for instance, T is a copper constantan thermocouple, so on and so forth. And you see the different temperature ranges for these different. But all of these are the junction of two dissimilar metals with a corresponding reference junction, and then an EMF is generated, predictable according to the Seebeck effect, and actually can be used to measure or relate to and display the temperature of the particular measurement. Now, thermocouple extension leads to we just run thermocouple wire from if we have a thermocouple in the field and we want to maybe run that back with some extension wires 100 to 150 feet back to a instrument with a reference junction, is that copper wires that we want to run? No. We, again, on the standard, we can find which ones are the most to be used. Look up your type of thermocouple. Here's an iron constantan. Then my extension wire I should use is a type JX, which happens to be iron constant. But also there's other like chromel alumel. Look it up, and maybe the WX type or iron cuprinel can be used as well as a K. This is found in standards. This is found as how to install thermocouples and the type of wire that you have to have, and is very useful a reference. But one other point to look at here, notice the color codes on the different types of thermocouples, but notice that the red is always the negative lead. The red is always the negative lead, and that's true for all of the thermocouples. So you have a complete set like that, and physically they are installed as in a protection tube or a thermal well in most cases, and you have your thermocouple actually inside the protection tube, and again it can be brought out to a head and a junction area there. The protecting tube or thermal well is very critical in many applications. Most all thermocouples are put in one so you can remove them for replacement or maintenance. Of course, the insertion length is based on how big the tank or vessel is or what size line you're installing the thermocouple in. So this is all very critical of getting these at the right location to pick up the proper temperature. I would point out, too, there are some grounded thermocouples and some are ungrounded. The grounded means that the tip physically touches the bottom of the thermal well. The ungrounded, the tip is removed back a little bit. Naturally, the grounded thermocouple will give you a quicker or faster sense of a change in temperature. However, it can burn out or short out, so there's some drawbacks there. Most people, I believe, tend to go with the ungrounded unless it's a very critical temperature that you want to do everything possible to get a quick change. Temperature basically is a slow process. Our flow is quicker, pressure is quicker, level can vary depending on the size of the tank. Temperature is typically a very slow process. It takes time for the change to be made, for the temperature, for the heat coefficients to allow the temperature to be sensed by the thermal well, through the thermal well to the thermocouple. So sometimes people will use grounded just to speed up that type of response that they might be interested in. So the second type of temperature sensor we'll talk about is RTD, resistance temperature detector. And in this particular one, the resistance varies as the temperature changes, whereas on the thermocouple, the EMF or the voltage changed as the change in temperature. So here we see an RTD in a cutaway situation, and we have a resistance element, which many times is a platinum lead, and it's wound around a mandrel of some description, maybe a ceramic type mandrel. And as the temperature varies in this particular situation around this device, the resistance will change. And that resistance change is predictable to give you a output of 4 to 20 milliamps corresponding to a certain temperature range. So again, this is, and many industries use RTDs almost exclusively. This is showing what's called a Wheatstone bridge, a 2-wire RTD circuit. We see the RTD here represented as a resistor, that the resistance will change varying with the temperature, and this is put into a leg of the Wheatstone bridge. Now, the drawback to this is, though, the lead going out there and coming back will also have resistance, which will be not discernible to your electronic circuitry. So a 2-wire RTD has that drawback, and for the most part, you will see in industrial applications using a 3-wire RTD so that you offset or compensate for a portion of the lead resistance. You can go further to a 4-wire RTD, which compensates for all the lead resistance, and that is used a lot in labs and things of this kind. Normally, most of the time, I think 3-wire is what we see primarily in the industrial world as far as applications are concerned. A special case of a RTD is called a thermistor. There, the electrical resistance of the material varies greatly with temperature. The thing you'll see these a lot installed where you have limited spans, fairly low cost. You want some high accuracy and stability, and low to medium temperatures. In other words, you will see these as part of OEM supply. You will see these embedded in the windings on motors. You'll see them installed in switchgear. They're economical, so most of the time it's part of an OEM supply, but it could be applied in other places also. Now, just like we had a little sensor comparison chart for the flow type devices, for level measurement devices, this is a sensor comparison for thermocouples, RTDs, and thermistors, where you look at different characteristics, range, accuracy, so on and so forth, and determine some of the good and bad parts of the particular device. For instance, as far as linearity, you can see that the thermocouple is highly nonlinear, RTDs somewhat nonlinear, and thermistor is highly nonlinear. So, but when you get to ruggedness, the thermocouple is more rugged. So you look at all of these as far as comparing the attributes or the relative, how they relate to different types of quality of use. This particular, you can find these in other places. This is just one that we happen to have, so I wanted you to have a sensor comparison chart that might be of some use to you. So again, here's some quick selection that points out the key items to consider. RTDs, they're stable, they have broad temperature ranges, they have a more linear curve than thermocouples, highly sensitive, pretty accurate reading over there. Thermocouples, though, look how they go up to extremely high temperatures, very rugged, are small in size, and probably has a lower initial cost. Again, these are some of the relative pros and cons of these different types of devices that I wanted you to be able to see. Finally, a type of device you'll see occasion, sometimes installed, sometimes handheld, as a radiation pyrometer. And basically, if you're not familiar with that, just briefly, you have a situation of radiation, infrared radiation emitted from the target. It can be picked up back by a sensing head and converted to a corresponding temperature. Now, in ideal situations, it works very well. It can sense temperature of moving objects, like on a conveyor belt or materials coming out of heat treatment or something like that. However, the problems you can run into that you have to be careful of is in real world, look at some of the things that you can get involved with. So you have to be very careful on the installation and the use. They're very, very handy. They do a good job, particularly for moving objects and things like that. But be aware that such a device does exist, is in use, called a radiation pyrometer. Now, there's many different types of RTDs and many different types of thermocouples that we have not had a chance to go over. This is just to give you a flavor of some of the things that could be some key points that you might have to be aware of. The different scales, the fact that time lags are involved, it's a slow measurement. You've got to look at, again, all the application considerations and the chart. So they might have you, again, they give you a scenario of what's going on and ask you to select the proper one. And we primarily focused, again, on thermocouples and RTDs because these are two of the very primary ways that we measure temperature. So we've had to breeze through that, but I think we've covered the high points. And let's pause one more time for if there's any questions before we go through some sample problems. So, Benita, I'll throw it back to you.
Thank you. And again, press star 1 on your telephone keypad to ask a question. Mr. Wilbanks, there are no questions at this time.
All right. Thank you very much. And let's move on along. Before we get into the sample problems, so I'd like to get you to do me a favor, if you would. How about tell us how many people are at your particular site today, so we'll have a record of the attendance and sort of how many people were involved. So if you could do that for me briefly, I would definitely appreciate that. And we just get that for our records and everything. I believe we have everybody recording now, so we will go back to the final part of our presentation today. Thank you very much, and we'll move to a few sample problems. Now, let's see how some of these might look on a test. Sample problem number 1, we have a tank level measured using differential pressure transmitter, and here's that old bubble tube. The tank is vented to the atmosphere. The bubble tube is a foot from the bottom. Tank wall is 20 foot high. We've got a 0 to 10 psig differential pressure gauge accurate to 0.25% of full scale, connected to the bubble tube and to the high side of the transmitter. The low pressure side is connected to the tank top, with the tank containing the liquid, specific gravity of 1.2, and the level of the tank at 14 feet. The gauge reading in pounds per square inch is most nearly equal to. And we got 4 answers there. And always read the question very carefully. Take it apart. Look at your units a little bit. Don't jump in there too quick. And also, sometimes they'll just give you some extraneous information, but sometimes it might be useful. For instance, here, I don't really care about the accuracy of my particular gauge. I also don't care that the low pressure side of my transmitter or sensor is connected to the tank top because it said this is a vented tank. I do care that specific gravity is 1.2, that the level is 14 feet. However, one thing I would point out here said a 0 to 10 psig differential pressure gauge is connected to this thing, and one of the answers, if you look down here, one of the answers is 13. Therefore, it's pretty unlikely that I can have a 13 readout with a maximum point of 10 psig. So how would I do this? And if you'll excuse my typing a little bit, let's just say the pressure we're going to look at is going to be equal to, and it's 14 feet in the tank, so my bubble cube, though, is 1 foot from the bottom, so I'm actually looking at 13 feet of liquid in the tank. But is that all I need to know? What else is important? I've got to take into account the 1.2 specific gravity. That's going to give me 15.6. Well, I don't see an answer 15.6 over there, so ooh, I'm in trouble now. But what is the units on my 15.6? Right, it's feet of water. That's what I'm looking at, 15.6 feet of water. Well, now what do I need to do? Well, I need to say that actually my pressure is actually 15.6 times, here's one of them nasty conversion factors. I've got feet, and what am I going to do with that? Well, there's a factor 0.433, which is actually PSI per foot of water, okay? So if I multiply these two out, I get P is equal to 6.75, according to my calculator that I punched it out on. And what's the units on that? It is PSI. Now, what are the units over here to the side? These are PSI on answers A, B, C, and D. So if I use that as a basis, then my answer would be D, 6.8. Now, I mentioned before, don't worry about the fact that 6.75, it's pretty close to 6.8. So work it out like that, okay? Very good. Now that takes care of that. Let's go to another one. Okay, this is one dealing with temperature, and I don't know that you'll have a thermometry question, but just real quick, this is a thermocouple, and we're told that it's linear. And you say, well, you told us a little while ago thermocouples are not linear. Well, they're not, but if the problem says they're linear, okay? So 0 degrees F to 300 degrees F, and the element generates a filament voltage at 212, you got 9 volts, at 50, you got 0.9. If the thermocouple voltage is 1.9, the temperature indicator in degrees F should be blank, A, B, C, or D. Well, let's look at one thing right off the bat. We like to eliminate things that are impossible and may help us reduce the number of answers we're looking at. For instance, here, if I'm going from 50 at 0.9 and going up to 1.9, if I just know that the temperature is going to increase, I can rule out A and B. So I can look at that and just say, hey, I know my temperature is going to go up, so it's not going to be 20 or 38. So now I'm down to halfway, but we don't really want to do that. We'd like to do it a different way. So what we do on this particular situation is we'll set this up and just say, okay, I want to know my new temperature at 212. If I compare it to my new temperature, and say that, well, first I've got to get a relationship between the two. Let me go back up and do this a different way to make sure we get this right. We've got 160 2 degrees that's going to be represented linearly by a change of 8.1 millivolts. So if I look at that on a situation, I'm going to get a representation of 1 millivolt is going to equal to, I unitized it a little bit, that's going to be equal to 20 degrees. Okay? Well, in this case, I went from 0.9 to 1.9, so I'm going to be 20 degrees up from my starting point, which was 50, and if I add, if I take that and add the 20 degrees to it, I'm going to end up with a, I'm going to end up with the final answer of 70 degrees, and that happens to correspond very nicely to answer C. So this was just a case of mathematics, just saying, well, for every millivolt is 20 degrees, or 20 degrees per millivolt, or 0.05 millivolts per degrees F, however you want to do it, and you can work it out by just using a relational basis there. So basically you work it out, and this particular one was just mathematics, but the point is here, I wanted you to see, be sure, and delete these obviously incorrect answers, and then that gives you a better situation of working the problem. Number 3, measuring the liquid level with a dielectric constant greater than 2 and a horizontal vessel changing composition temperature in the device with the best reproducibility is a guided wave radar level detector, ultrasonic level detector, capacitance, or differential pressure. Well, some of these are scenario problems. Notice here they gave us a dielectric constant greater than 2. That's going to bring the radar into play there a little bit. Notice we have a changing composition and temperature. That's going to give us a varying specific gravity. That's going to give us a varying overall composition that will rule out, for the most part, it'll rule out differential pressure. It'll really take out the capacitance level detector, would not be wise. And the ultrasonic level detector might be a good situation, but you have to look at the varying environmental considerations there. So I think in this particular case, and some of these are sometimes debatable, but in this particular case, the guided wave radar level detector, because you do have a dielectric constant heavier than, more than 2. If it had said a dielectric constant of 1, for instance, the answer would have been ultrasonic level detector. Now, ultrasonic level detector would probably operate here, and some of you are probably saying, well, we use that at our place right now. I put those in. Sometimes they try to make the distractors, I'd say, distinguishable, but also they want them not to be ridiculous. So some of these are a little bit subjective, and probably on the exam they could be the same way. But in this case, that would be the most appropriate answer. Number 4, another scenario question. Which of the following flow meters can be used to directly measure the volumetric flow rate of a fluid? Differential pressure, magnetic, positive displacement, turbine, and vortex shedding. Of these, which one directly will measure the volumetric flow rate? If you recall, we said the positive displacement would. Now, you say, well, no, wait a minute. I thought you said we use differential pressure orifice place to measure volumetric flow rate. Well, we do, but we measure differential pressure. What do we measure with magnetic flow meters? The velocity. What about turbine flow meters? The velocity. What about vortex shedding flow meters? The velocity. And that's all based on the fact of that relationship that we talked about Q is equal to AV. So what we do in many cases, we actually measure the velocity, we know the area, and that can be used then to actually give us the volumetric flow rate. But in the case of the positive displacement meter, it measures the volumetric flow rate directly, and that's what this question asks for. Okay, so some questions are just knowledge-based, and you just hope they're the ones that you know very well and that you can answer. So that's what you're looking for. Okay, number 5, real quick. The flow of water in a 4-inch pipe is measured with an orifice plate and differential pressure transmitter. At a flow rate of 120 gallons a minute, the differential pressure is 27 inches of water. At a flow rate of 176 gallons per minute, the differential pressure will be approximately equal to 12, 18, 58, and 68. All right, look at your question, read it carefully, understand the question. First of all, we start out at 120 with 27 inches of water differential pressure. And then we're going to 176, and we want to know what the differential pressure will then be. Well, first of all, let's say we're increasing our flow. In what direction will our differential proceed? You say, well, it's going to go up, and you're exactly right, and that's why we know it's not going to be 12 or 18. So we just reduced ourselves to 2 answers, even if we had to guess. And one of my favorite guesses is C. Charlie anyway, but we won't guess on this particular one. We're going to actually go ahead and work this one out. And what we're going to do is say, well, we got 176, and you know, we're going to put that over 120, and then we know that that's equal to, or it's going to be proportional to, and I can't do this exactly like I'd like to, but the square root of the x factor that we're trying to figure out, square root of x, and well, I didn't get that in there yet. Wait just a minute. It's going to be the square root, and we're going to have x divided by, I've lost my little situation here, divided by, and I'm making a mess of this, but anyway, 27, and I'll close that back out. The key factor here is to recognize the fact that the square root of the differentials are involved when you've got the relationship between the flow rates. Now, if you solve this one out, you will find out that x will equal to the a value of 176 divided by 120 squared. And if you go further, times the 27. You've got to solve the whole thing out, 27. And you will get an answer for the one that we're seeking. X is going to be equal to 58.08 in my case. And if you look back up at your selected answers, C is equal to 58. That'd be the correct answer. I apologize for my typing. The key point here is flow rate through a differential pressure producing device is proportional to the square root of the differential. So what we said at this point here was 176 is to 120 as the square root of the new differential divided by the old differential. Then if you solve for x, you get this, and the final answer is here. So that's an example from our differential pressure and our square root world that we have as far as differential pressure flow measurements are concerned. That pretty well wraps us up for today. I would like to remind you that there's plenty of information available from ISA on all areas of automation, control systems, and instrumentation. There's different classes that you can take and study. And, of course, a lot of the books are available from ISA or are available from other sources, as the case may be. You've got this already on your bibliography list, but we'd like to make sure we do tell you about that. And I'd encourage you, if you're not a member of ISA, to join. Be a member. You get a lot of benefits from it. And, of course, we do a lot of things, including the training sessions. We also sponsor support the Certified Automation Professional and the Certified Control Systems Technician, in addition to the Control Systems Professional Engineer licensure. Thanks so very much for being with us today, and I hope this has been somewhat beneficial. I know it's been a little bit long, but thank you very much, and I look forward to seeing you the next time. Bonita, I'll turn it back to you to close out.
This concludes today's ISA web seminar. Please do not forget to fill out the evaluation survey found in your email inbox. Thank you for attending, and have a nice day.